Okay, I decided next to jump ahead to lab 20 part 6.4, the switched capacitor filter, because I already had the 411 op amp in place from part 6.1. So I'll just skip ahead to the other exercise that uses the 411 op amp. So I circled pin numbers on the DG403 analog switch, and then I put little rectangles around pin numbers on the 411 op amp. And again, also I scratched out this indication to use a pull-up resistor to +5. That's just an artifact of the powered breadboard that Tom uses in his labs. Those are the same blue powered breadboards we have in our lab, but we usually don't use this feature. And I'm continuing to use just +5 and -5, so I don't need plus and minus 15, or I don't need the 9-volt battery. So that's so far so good there. So this is sort of neat. You can actually make a low-pass filter using a pair of switches and a pair of capacitors. And it's kind of like you have a little bucket and a big bucket, and you're kind of sloshing back and forth. You sample the input signal with the little bucket and then pour it into the big bucket. And then the ratio of the two bucket sizes times, I guess, how often you switch back and forth gives you a low-pass filter frequency. So it's actually kind of neat. And I guess one way to look at that is you can say the big bucket is sort of every time step. The big bucket is, let's say, alpha, some small number alpha. You call it epsilon. The new contents of the big bucket is epsilon times what's in the little bucket plus 1 minus epsilon times what's already in the big bucket. So it essentially has the same effect as an RC filter, but you can actually make a pretty good filter this way. So anyway, here is the circuit wired up, and I built this half an hour ago, so now I'm struggling to remember what's what. But this is the little capacitor, the 330 picofarad capacitor, going from pin 1 of the DG403 down to ground. I put the larger capacitor, the 10 nanofarad capacitor, over here. I had to put it over here because it doesn't have long legs that let me stretch all the way down to ground. So I just went from pin 3 of the LF411 op amp over 2 positions, and then I ran a jumper wire down to ground. And then here's this yellow wire, which is going from pin 3 of the DG403 over to pin 3 of the op amp. Let's see, then I have in yellow a signal source going into pin 16 of the DG403. And then yellow with a white stripe is my switch back and forth signal. So that's channel 2 of the signal generator going into pin 15, which is telling the first switch whether to be closed or open, and is telling the second switch whether to be open or closed. So the two switches, the two parts of the same switch, are in opposite configurations at any given instant. And then I'm probing, orange is the first scope channel, I'm probing the input signal, and I'm also probing with blue, the second scope channel, the output of the op amp. And let's see, then this is a really slow signal. So I'm using, let's see, so the waveform generator, I have 100 millihertz, that's a 10-second period, 0.1 hertz sine waves. That's my signal that I'm filtering. And then meanwhile, the switch back and forth signal is a 50% duty cycle, 1 kilohertz square wave. I'm going to leave this fixed, but I'm going to vary the frequency of the sine wave. So you can see if I go back to, and then my power supplies are +5, -5. If I go over to scope, you can see with a 10-second period, 0.1 hertz, that the input and output waveforms basically perfectly overlap, no phase shift. Now, if I go up to a 1 hertz input signal, and I go back to scope, oh, it takes it a while to update, especially on this. Okay, it takes a while to update because you have to accumulate a whole screen full of data. And let me zoom in now by a factor of 10 on the horizontal. So you can start to see a little bit of a phase shift here, just a barely noticeable phase shift, but pretty negligible attenuation. And then let's go another factor of 10 in frequency to 10 hertz. And back to the scope. Now we see a pretty good phase shift here. So I'll go to 20 milliseconds per division. And this looks like it's pretty close to F3 dB. I see something that seems like on the order of a 45-degree phase shift, and it looks like on the order, looks like a little, actually this is probably a little bit beyond F3 dB, because it looks like the attenuation is a little more than a factor of 1/√2. But it seems to me that F3 dB for this filter, I didn't actually try to calculate it yet, and I don't know if I'll have time before I run out of the 10-minute YouTube video limit, but so this is 10 hertz. So I'm going to guess F3 dB for this filter is a little less than 10 hertz. Okay, now let's go to 100 hertz. Go back to the scope. Oh, now you can see this is really severely attenuated. So then I'll go to 2 milliseconds per division. Yeah, so that's very highly attenuated. So, okay, my claim is that F3 dB is a little less than 10 hertz if we use 1 kilohertz as the sampling frequency. And I guess we can say, okay, C1 over C2 times F clock over 2 pi here. Let's try that. Let's see. Oh, I wonder if I can do this before math. M-A-T-H. Okay, so we'll say F sample is 1000, and we'll say C1 is 330 times 10 to the minus 12. We'll say C2 is 0.01 times 10 to the minus 6. Is that right? Yeah. And then we'll say C1 over C2 F sample over 2 pi. And okay, we get, it claims that F3 dB is about 5.25 hertz. So that seems pretty easy. Okay, well actually, what the heck? Let's go back to, let's do 5 hertz, and then we'll go back here and go to let's see, here's 1 second per division. Takes it several seconds to fill the screen with points. Has to fill its little memory with points, and then it fills the screen with points. Oops. I guess I want to go to here. Here's 100 milliseconds. Oh, okay, there we go. So then maybe even like that, 50 milliseconds per division. Yeah, I think you can argue that that's about a 45-degree phase shift, and that's about a factor of 0.707, 1/√2 basically, in amplitude. So that seems pretty plausible that F3 dB is around 5 hertz. Okay, so I think that's kind of cool. We got the switched capacitor filter working.